Welcome back to class. We're getting ready to solve polynomial equations very soon without them being in factored form. Two procedures or two rules that will help us in that effort for solving those equations will be the rational zero test and DesCarte's rule of signs. So today we're going to discuss those two methods, those two rules, procedures, and then in the next lesson we'll put it all together and we'll solve some polynomial equations. So by the end of the lesson, the student will be able to use the rational zero test to determine all possible rational roots of the equation or rational zeros of the polynomial function. It all depends on whether we're looking at an equation or a function. We want the roots of an equation or the zeros of a function. It's the same thing. It just depends on the context of which question is asked. Also, by the end of the lesson, the student will be able to use DesCarte's rule of signs to determine the number of possible positive and negative zeros a polynomial equation or function has. Okay, first up, the rational zero test. The rational zero test will give us all the possible rational zeros of a polynomial function. It won't tell us every zero in the polynomial that the polynomial has. It'll only tell us the possible rational zeros. Rational zeros, that's it. So what is a rational number? A rational number is a number that can be written as the ratio of two integers, a and b, such that a over b is a rational number where b does not equal 0. So you can write a rational number can be written as a ratio of two integers. Okay, yes, two integers is a fraction, but I don't want to say a rational number is any number that can be written as a fraction, because that is a fraction. Okay, 3 over pi, that's also a fraction. 6.5 over 2.9, that's a fraction on top of a fraction. That's a complex fraction. These are fractions, but they're not irrational numbers. All right, so that's why I didn't just say any number that can be written in terms of a fraction. No, it's any number that can be written as a ratio of two integers. If it's a decimal, the decimal, let me clean that up a little bit. So if our number is a decimal, the decimal must repeat or terminate. Those are the rules for rational numbers. Any number that can be written as a ratio of two integers, and if it's a decimal, the decimal has to repeat or terminate. Okay, to find all possible rational zeros of the function, we're going to use, here's our function, here's a polynomial function in general form, and we're concerned with the number at the back here, which is the constant, and we're concerned with a, the leading coefficient. What happens in between does not matter. All we're looking for is all the possible rational zeros. So what happens here doesn't matter. Even that sign isn't important. We care about the numbers. That's all we care about. The reason the sign isn't important is because we're going to put plus or minus anyways, and you'll see what we do with that. So To use the rational zero test, what we're going to do is we're going to take the factors of the constant, k, and we're going to take that over the factors of the leading coefficient. So all of the factors of this number over all the factors of this number. And then what we're going to do is from that list of factors on top of factors, we're going to rewrite it and create an overall list. And that list will give us all the possible rational zeros. Okay, so let me show you what that looks like. We're going to find all possible rational zeros of this function. So what I want is I want the factors of 25 over the factors of 2. So I got to list those out first. What number is multiplied by 25? That's plus or minus 1, plus or minus 5, plus or minus 25. You see, that's why we don't care about the sign, really. It's a negative 25, right? Well, that could be a positive 5 and a negative 5. And that could be a negative 5 and a positive 25, or it could be a positive 1, or it could be a positive 1 and a negative 25, or a negative 1 and a positive 25. So that's why we're just going to use plus or minus, so don't worry about the sign. Always put plus or minus. So these are all the factors of 25. The factors of 2, plus or minus 1, plus or minus 2. Okay. Now, what are all possible rational zeros? What we're going to do is you're going to take each one of these factors and put them all over 1. Then you'll take each one of these factors and put them all over 2. So I have plus or minus 1, plus or minus 5, plus or minus 25. Okay, first of all of these over 1, they don't need to be written as fractions because they're just over 1, over 1, over 1, over 1. Don't need the 1 there, right? Now all of them over 2. Plus or minus 1/2, plus or minus 5 halves, plus or minus 25 halves. That's it. We take each of these over 1, then each of these over 2. We'll write the list. This is the list of all possible rational zeros. All right, so when I ask you to find the zeros of these functions, you can try any number you want to see what would work. You remember, we use synthetic division to verify a zero, or synthetic substitution. We've already discovered synthetic substitution when we talked about the remainder theorem. So we'll be using synthetic substitution to check these numbers. If I don't have a list of possible rational zeros, then literally any number from negative infinity to positive infinity you could work with, and it would take you forever to try to solve the problem. This gives you a solid list of where to start. Okay, so let's look at number 2. Find all possible rational zeros of this function. All right, we need the factors of 15 over the factors of 6. Factors of the constant over the factors of the leading coefficient. Constant, leading coefficient. So what numbers multiply to 15? What numbers go into 15? 1 does. 2? No. 3 does. Does 4 go into 15? No. 5 does. So 5 is a factor of 15. And 6, 7, nope, just 15. Those are all the factors of 15. So in other words, those numbers all go evenly into 15. Okay, what are factors of 6? Obviously, 1. Does 2 go into 6? Yes, it does. Plus or minus 2. Plus or minus 3. 3 goes into 6. 4? No. 5? No. 6 does. Okay. So possible rational zeros, all of these now over 1. So plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Now we take all 4 of these over 2. If anything repeats, you don't need to write it again. Okay, plus or minus 1/2, plus or minus 3/2, plus or minus 5/2, plus or minus 15/2. Okay, now over 3, plus or minus 1/3, plus or minus 3/3. I'll go ahead and put that right now. Plus or minus 5/3, plus or minus 15/3. Now let me stop here for a moment. We still need to get to the 6, but we'll get to that in a second. Notice 3 over 3 is 1, right? And I already have 1. So since I already have 1, I don't technically need to list that because I already have it. 15 over 3 is 5. I have 5 already. So if I already have 5, I don't need to list 15 over 3. So you can omit those. If something repeats, you don't need to write it again. Just leave it out. Okay. So plus or minus 1 over 6. Now 3 over 6. 3 over 6 is 1/2. Do I have 1/2? Yes, I do. I already have 1/2. So I don't need 3 over 6. So let's go ahead and skip that. I do need plus or minus 5/6. 15 over 6. Let's see. 15 over 6 would reduce. 3 goes into 15 5 times. 3 goes into 6 twice. Do I have 5/2? Yes. So I don't need to put anything else. This is our answer. Those are all the possible rational zeros. Okay, now let me tell you, if you went ahead and still wrote those out, I'm not going to mark it wrong. That's fine. Even though I don't need those, if you went ahead and put those, if you went ahead and put down 1/2, plus or minus 1/2, and plus or minus 15 over 6, that's fine. I'm not going to mark it wrong. Okay, make sure all the zeros are accounted for. Your answer can never be this green, this one in this form in green. Your answer must be all these individual fractions when I ask for all possible rational zeros. Okay, here are a couple of variations of the question. Which of the following is not a possible rational zero of the function? Which is not a possible rational zero of this function? Is it A, -12, B, 18, C, -8, or D, 3? Okay, hopefully you all put down B, 18. First of all, these are all whole numbers. So that means the denominator must be 1 that I'm talking about. Maybe, may not be, but there's a denominator, right? There's a numerator, leading coefficient's 1. So I'm looking at the factors of 28. Which of these, that's all I'm really asking here. Which of these is not a factor of 24? That's really what this question is asking. Not a possible rational zero, that means it must not be a factor of 24. 18 is not a factor of 24. 12 goes into 18, or -12 goes into -24. -8 goes into -24. 3 goes into -24, but 18 does not. It's got to go in evenly, remember. So that's a small variation to that question. Here's another one. If you notice, these are a little more Common Core-ish than the other. The others are real straightforward. These are kind of coming at it from a different direction, a little Common Core. The following is a list of some of the possible rational roots for the polynomial expression, for a polynomial expression. These are some of the roots for a polynomial expression. Based on this list of possible rational roots, determine which of the following could not be the polynomial expression described. Circle your choice. So based on those roots, go ahead and put the video on pause and decide which one of these could not be the polynomial represented that has some of these roots. We're going to check it in just a second. Okay. So I'm focused entirely. Look at all these leading coefficients. Let's make sure to look at the exponents. They are all in decreasing order. That's good. Leading coefficients for all of them is 1. So what I'm really concerned with is the constant. 36. Are all of these numbers factors of 36? Yes. Are there more factors of 36? Yes. But these are only some of the possible rational zeros. So these all count for 36. How about 72? Yes, yes, 72, yes. Does 4 go into 72? Yes, it does. 6 times 12, 12 times 6, yes. 54. 2 goes into 54, 3 goes into 54, yes it does. 4 does not go into 54. 54 divided by 4, 1, 3. I have a remainder. The answer is C. Because 4 is not a factor of 54. These are all factors of each of these numbers, 36, 72, and 24. That's the only one that doesn't fit. That's odd. It just doesn't fit. Not all of these are factors of 54. They all should be. Okay. You see, this isn't real straightforward. This is a Common Core question. So make sure you can answer that. Okay, on to DesCartes' rule of signs. DesCartes' rule of signs can tell us how many possible positive or negative roots or zeros a polynomial function or equation has. This tool is not necessary to solve the polynomial equation, but can help make us more efficient in the process. So in other words, technically you don't have to use this to solve polynomial equations, but it actually could help. Okay, like I said, you're going to be listing all possible rational zeros. For example, this one. These are all the possible rational zeros for number 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2, because it's plus or minus. There are 24 possible zeros here. This is 24 possibilities. Well, what if I use DesCartes' rule of signs, and DesCartes' rule of signs told me that there are 3 possible positive zeros and 1 negative zero. 3 positives and 1 negative zero. Well, then, if that were the case, then wouldn't it be more efficient to try to pick positive zeros to see if those work first? We want our work to be efficient. You have a greater chance of a positive zero working than you do a negative zero. So the DesCartes rule of signs could make you more efficient in that way, because you're going to choose, it'll help you choose numbers, choose your zeros. And you'll see what I mean when we start solving the equations. So what we're going to do is we're going to set up a table when we do this. We're going to set up a table with positive zeros, negative zeros, and imaginary zeros. Now, one thing when you set up the table that you're going to notice, and as we do this, for the table, each row must add to be the degree of the polynomial. So if we're talking about a 5th degree polynomial, each row is going to have to add up to be 5. Okay, the rows add up to be the degree of the polynomial. This column here always have even numbers. always evens in imaginary column. Why is that? Hopefully you're already thinking about it. The reason that this always has to be an even number is because your complex roots always come in conjugate pairs. Always. So you get something like 3 plus or minus 2i. So there's 2 zeros there. You can't just have 3 minus 2i. 3 plus 2i must also be 1. So that's why the numbers in this column are always going to be even. You don't know what these are going to be. You don't know what those solutions are. There's nothing to help you with those, because all you'll know is the rational zero test will give you all the possible rational zeros. Okay, the imaginary zeros we won't know. So as we use DesCarte's rule of signs, our table will be created like this. It's going to show the possible combination of roots that are possible. We set up a table in this manner. This will help us keep track of the number of possible positive roots, negative roots, or complex roots of the equation, or whatever the function may be. Okay. I'm never going to ask you for the table on a test or quiz. On a test or quiz, I'll just ask you, according to DesCarte's rule of signs, how many possible positive zeros are there, or how many possible negative zeros. You'll see just like the questions here. I'll ask you. So don't worry about the table. The table can be a little tricky. Don't worry about that. Okay, DesCarte's rule of signs. DesCarte's rule of signs says that the number of positive zeros can be found by counting the number of sign changes in the problem. The number of positive zeros is that number or less by an even integer. Okay, so what we're doing is this. We're looking at the polynomial function. We're going to go from left to right. You read from left to right, just like you're reading a sentence. Read from left to right. Count the number of sign changes in the problem. So this is positive, right? Now it goes to negative. So there's one sign change right there. Positive to negative. Negative to positive, 2. Positive to positive. Positive to negative, 3 sign changes. Negative to positive, 4 sign changes. Positive to negative, 5 sign changes. So you should have noticed that there were 5 sign changes as I read the signs from left to right. What that means is the number of possible positive zeros is 5, 3, or 1. Can you guess what the most common mistake is students make when I ask this question? The number of positive zeros is that number or less by an even integer. They forget this part. So once you get the number of sign changes, what you're going to do is you're going to keep subtracting by 2 until you hit 1 or 0. Then you stop. So 5, subtract by 2, you get 3. Subtract by 2, you get 1. Stop. You keep going until you hit a 0 or 1. Then you stop. So let's say for another example, there are 6 sign changes. So let's say we do it again, and this time there are 6 sign changes. So in that case, there are 6, 4, 2, or 0 possible positive zeros. 6, keep subtracting by 2 until you hit 1 or 0. So 6 minus 2, minus 2, minus 2. Now you stop. Okay. So again, now DesCarte's rule of signs for negative zeros. The number of negative zeros can be found by evaluating f of negative x. Count the number of sign changes in f of negative x, and the number of zeros is that number or less by an even integer. Okay, so remember, what does this mean? Evaluate f of negative x. Plug in negative x. That's what that means. Plug in negative x. Substitute it. So I'm going to go ahead and I'm going to substitute. And hopefully you remember this. F of negative x. We did this before when we were talking about whether a function is even or odd. Remember, when does the sign change? When you plug in a negative x, which one of these will the sign change for? Only when the power is odd. So this will stay the same. That's going to be positive. This one's going to change. Odd degree. So this is going to become positive. Positive stays the same. It's a positive 4. It's an even degree. So that stays the same. Plus. This changes. Minus. Even degree stays the same. Minus. Odd degree changes. Minus. Constant. The constant does not change. Okay. So remember, signs only change for odd exponents. When plugging in negative x. So when you plug in a negative x, the signs only change for the odd exponents. Okay, so we're going to count the number of sign changes. Pay attention to this line only. That line only. Read from left to right. Only from that line. In other words, what I'm trying to tell you is this. We're talking about when we plug in a negative x, how many sign changes are there? Not from this equation to this equation. We're not talking about changes going this way. We're talking about changes going this way within the problem. There is only one sign change. Only one sign change. So there must be one negative 0. Okay. Now look, that's what we just talked. This is the same function, I believe. It's the same function. Okay, so I had 5, when I was looking for positive zeros, I had 5 sign changes. So the number of possible positive zeros is 5, 3, or 1. The number of possible negative zeros is just 1. So what that would mean is if I was setting up a table, here's how it would look. Positive, negative, imaginary. How many possible positive zeros would there be? Okay, well, the number of sign changes was 5, so there would be 5, 3, or 1 possible positive zeros. Okay, there must only be one negative 0. There must be a negative 0. So there's only one negative 0. Now from this, we have to fill out the last column. Each row, remember, must add up to the degree of the polynomial. Well, this was a 6th degree polynomial. So 5 plus 1 is already 6, so nothing happens here. 3 plus 1 is 4, so this must be 2. 1 plus 1 is 2, this must be 4. Now each row adds up to 6 because there are 6 zeros. So what we're saying is there could be, to this polynomial, there could be 5 positive zeros and 1 negative zero. There could be 3 positive zeros, 1 negative zero, and 2 complex zeros. Or there could be 1 positive zero, 1 negative zero, and 4 complex zeros. All right, so when you're picking for synthetic substitution, you want to see which one of these is actually a zero. Doesn't it make more logical sense to choose a positive zero, positive number? So when we list out all the possible rational zeros, we're listing out positives and negatives. We only want the positives because there's a greater chance of one of those working. Okay. All right. Let's put the two processes together and find all possible rational zeros of the functions below and determine the number of possible positive and negative zeros each function has. Okay, so we're doing it both at once here. So I need the factors of 25 over the factors of 2. And that's plus or minus 1, plus or minus 5, plus or minus 25. And factors of 2, plus or minus 1, plus or minus 2. Okay. Possible rational zeros are plus or minus 1, plus or minus 5, plus or minus 25, plus or minus 1/2, plus or minus 5 halves, plus or minus 25 halves. And now let's find out how many possible positive or negative zeros. Let's see. We'll do this in red. Possible positive zeros. Possible negative zeros. Okay, how many sign changes do I have? Positive to negative, 1. Negative to positive, 2. Positive to positive. Positive to negative, 3. I have 3 sign changes. So how many possible positive zeros are there? 3 or 1. Okay, negative zeros. Okay, f of negative x. Let's plug in a negative x. Nothing changes, so that's positive. Changes, positive. Even degree, nothing changes, positive. Odd degree, changes, negative, negative. Okay, how many sign changes? Just 1. So there must be 1 negative zero. All right. Okay, that's what I'll need on the test. I won't need tables. I just need a list from you. You can do the table if you want to help you out. Okay, here's number 6. Okay, once again, we want all the possible rational zeros, so I need the factors of 32 over the factors of 10. So factors of 32, plus or minus 1. 2. 3 does not go in there. 4 does. 5, no, 6. 8 does. 2 goes in there 16 times. And 1 goes in there 32 times. And the factors of 10 are plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. So this is going to be a big list again. So all of my possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32. So all of those over 1. Now going over 2, 1/2. 2 over 2 is 1, I've got 1. 4 over 2 is 2, I've got 2. 8 over 2 is 4, I've got that. 16 over 2 is 8, got that. 32 over 2 is 16, I've got that. So now let's go to 5. Plus or minus 1/5, plus or minus 2/5, plus or minus 4/5, plus or minus 8/5, 16/5, 32/5, nothing to help me there. And then 10 plus or minus 1/10. 2 over 10 is 1/5. 4 over 10 is 2/5. 8 over 10, 2 goes into that, that's 4/5. 16 over 10, that's 8 over 5, 8/5, that's covered. 32 over 10, 2 goes into that 16 times, 2 goes into that 5 times, just 16/5. Okay, here are all the possible rational zeros. Now, let's look at the possible positive zeros and possible negative zeros. Okay, sign changes. Positive to positive, positive to negative, there's one. Negative, 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 negative. Only one sign change. So there's one possible positive zero. Okay. If I evaluate, this isn't f of x, this is g of x. So g of negative x, if I plug in a negative x, does this one change? Yes, it does. Odd degree, so that becomes negative. Even degree, no change. Odd degree, changes. Even degree, no change. Odd degree, changes. Constant, never changes. Okay. So when I evaluated g of negative x, counting the sign changes, 1, positive, 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 negative, negative, positive, positive, negative. 1, 2, 3, 4 sign changes. 4 sign changes. So how many possible negative zeros? 4, 2, or 0. Keep subtracting by 2. Okay. I'm going to have you put the last one, I'm going to have you put the video on pause and do this last one on your own, then we'll check it. But before then, what do you notice here? You should notice right away there's no constant. Okay, so how do we handle this if there's no constant? Because I'm going to want to be able to find all the zeros of this function. Now, this doesn't exactly fit into this problem, okay? This is something that we're kind of foreshadowing a little bit. I'm just kind of showing you what you're going to face in the future. You're going to have to solve this polynomial equation. You're going to get 6 zeros, but you don't have any constants to go by. So what does that mean? What that means is this. First is you factor out an x, and then it becomes 15x to the 5th plus 25x to the 4th plus 69x cubed plus 115x squared plus 36x plus 60. See, and then when you set these equal to 0, one of your zeros, one of your solutions to the equation is 0. And then you set this one equal to 0, and then you have to go through the process we just did. Okay, so we need to find all possible rational zeros. We're going to use the constant of 60, or the factors of 60 over the factors of 15. So list those factors out, then find all possible rational zeros. And then tell me, according to DesCarte's rule of science, how many possible positive zeros and negative zeros there are. Go ahead and put the video on pause and get that done now, and then we will check it in a moment. Put the video on pause now. Okay, first, here are the possible rational zeros. That's a very long list. So I want to say this very slowly to make sure you should have all of them. Okay, first of all, you need the factors of 60 over the factors of 15. Now, there are a lot of factors of 60 and 4 factors of 15. All right, so you should have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 12, plus or minus 15, plus or minus 20, plus or minus 30, plus or minus 60. So those are all the factors of 60 over 1. Now the fractions, plus or minus 1/3, plus or minus 2/3, 2/3, plus or minus 4/3, plus or minus 5/3, okay, plus or minus 10/3, and plus or minus 20/3. Those are okay. Next fraction, plus or minus 1/5, plus or minus 2/5, plus or minus 3/5, plus or minus 4/5. Don't need that. Plus or minus 6/5, plus or minus 12/5. And then 5 goes in all of those evenly. We've got those already. 15. Plus or minus 1/15, plus or minus 2/15. 3/15 is 1/5. Don't need that. 4/15, plus or minus 4/15. I've got 1/5. 6/5 reduces down to 2/5. So I have 2/5. Don't need that. Don't need that. The rest were okay. Those are all the possible rational zeros. Okay. Now let's do DesCarte's rule of signs. Possible positive zeros and possible negative zeros. So let's see what DesCartes has to say. Okay. Counting number sign changes, positive, 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 no sign changes. How many possible positive zeros are there? None. There are no possible positive zeros. So if you were to try to solve this, don't try any positive numbers, right? Because no positive numbers work. Only try negatives. Okay, let's plug in a negative x and see what happens. So h of negative x, this stays the same, so it's still positive. Changes, negative. Stays the same, positive. Changes, negative. Stays the same, positive. Changes, negative. 1, 2, 3, 4, 5 sign changes. 5 sign changes. So how many possible negative zeros? 5, 3, or 1. Now, let's see, does it make a difference if we do it from here? Because that would probably be more appropriate from here. First of all, positive zeros. Let's ignore that. Positive zeros. Does it make any difference? No. No sign changes. Let's try negative zeros. That becomes minus, stays the same. Minus, stays the same. Minus, stays the same. 1, 2, 3, 4, 5 sign changes. Same thing. 5, 3, or 1. Okay. It's going to take a little while to get the hang of this. But like I said in the notes a little while ago, DesCartes' rule of signs is not necessary to solve polynomial equations. The rational zero test is necessary, but you can always solve the equations without DesCartes' rule of signs. It just helps you be more efficient. Okay, so make sure, at the very least, you understand rational zero test. You can find all possible rational zeros because everything's going to hinge on that when you solve the equations. All right, regular IM3, if you're not too good with DesCartes' rule of signs, that's not a big deal. IM3 honors and above, you should understand how to use DesCartes' rule of signs. All right, until the next time, it's Evil.chs.mathteacher signing off.